1, 2, 3.
Okay.
Testing.
Yeah, now it's picking up.
Okay, we're on?
Yeah. You should turn the sound off on your
Mute.
computer there.
There.
Okay.
All right.
All right, we are...
We're recording. We're going to full screen.
We're crossing our fingers.
Okay, Mark, take it away.
Excellent. Okay, thank you. Okay, so I'm going to be talking about a particle resampling method, which I'll explain a little bit. This is work in collaboration with Matt, so Professor Nepoli from here, and two of his ex-students, Danny Finn and Joseph Putze, are involved in this as well. So before I get into the main part of the talk, let me give a little bit of background on... a little bit of background on particle methods and kinetic models. So PDEs can be discretized with particles as well as the more familiar, I think, with this crowd, continuum methods. You have convergence rates, you have basis functions, you have weights that are on these or scales that are on each of these basis associated with the basis functions. This is not molecular dynamics. Each particle, people will say marker particles, is not an individual ion or electron, for example. And so particle methods have the advantage at higher dimension. So a simple kind of model shows that a crossover is at 4D, that the complexity sort of is tied at that point. And then when you go higher, particle methods are better. And this is a very simple model. This is maybe one way of looking at why you never see people use particles for 3D, CFD and MHD types of problems. And so our interests are in kinetic methods. So these are methods that are in up to 3 spatial dimensions and also 3 velocity dimensions, so up to 6D. Particularly, we're interested in magnetized plasmas, the Vlasov, Maxwell or Vlasov-Poisson Landau system. So the governing equations for this are the Vlasov-Maxwell or Vlasov-Poisson. It's got a Hamiltonian, so you're evolving each species in phase space, so X and V. And it's a Hamiltonian, so it's a total derivative is equal to 0. You expand that out, you get the term here, which I'm not going to go into details here. If you have a collision operator, you can put a collision operator on the right-hand side, or evolve the collision operators separately, which is how they're computed, where you sum over all of the species and interact with it with a collision operator, including yourself. And so the Vlasov and the Landau part are evolved separately. And so since they're evolved separately, you can mix particle methods with continuum methods, which is something that I've been working on for a while. And this work sort of grew out of that, as you'll see. Okay. So now we'll get into the body of the talk. So first, I'm going to give a little bit of background on conservative particle and grid function mapping. This is work that we published a few years ago that Joe led. I spoke about it here a few years ago. And then I'll talk about the algorithm, and then I will finish off with some numerical experiments using Danny Finn's Landau damping code. Okay, so... So many particle methods have grids associated with them, the well-known particle and cell method. And so in that context, you have to have a representation of your distribution function in both particles and on a grid. Ideally, you'd like those two representations to be identical. That's not possible, but you can make them equal in a weak form with a common process of convolving or integrating test functions against both distribution or both functions, and then setting those equal to 0. And so, and when you do that, you'll get in matrix form, you'll get a finite element mass matrix on the left. Do my arrows work here? So you have a finite element mass matrix times a coefficient of finite element coefficients is equal to a particle mass matrix times the particle weights. And so what's the finite element mass matrix is a standard thing. It looks, but the particle mass matrix is new, and that's integral over the domain of your test function, phi, times your shape function for your particle. And we'll be using delta functions, which makes this particularly simple. You simply are evaluating the finite element shape function at the particle position, and so the particle mass matrix is just a matrix of simple interpolants, so it's very simple. And so with that, we can solve this simply solve this equation here to have an expression for depositing particles onto a finite element grid. And when you do that, this is provable that you can serve all moments up to the degree of the polynomial that's represented exactly in your continuum space. And so you're going to see that a lot here because that comes up in several places. Okay. And so a quick overview of the particle and cell method. First, you deposit your particles onto the grid. You then do a Poisson solve, let's say, for the electric field potential, or an Ampere's law solve for the magnetic field potential. And then you compute electric and magnetic fields at particle positions. And then you push particles. That gives you a force, electromagnetic forces on the particles, and use that to push your particles to evolve your particle state. Okay, so if you've got a Landau collision, or if you've got a grid-based collision operator, then you would follow this, or you would separately do evolve your collision operator, and it starts off with the same process, putting it onto a grid. Now, this is a velocity space grid for collisions, and then you evolve your collisions on your grid, and then you need to be able to map your state back to your particles. So how do you do that? Well, the structure-preserving community in a community of mathematical physicists came up with a very embarrassingly simple idea of you just take this the function that you had for the grid deposition, and you simply invert it, and you get the v negative 1 m rho. But V is a rectangular matrix, and they use a pseudo-inverse, which makes their proofs work. And so you have a pseudo-inverse that has this expression, this form. And when you do that, you can prove that you have conservation in the same way that you have for deposition. And so these are very well-conditioned solves. We can use LSQR, for instance. It's just a black box Krylov method. Is what we'll use in practice. It converges very quickly. And again, this conserves all of the moments exactly. So this has an interesting property that it's idempotent. So let's consider just mapping your particles onto the grid and then mapping it back. So physicists call this coarse graining. It's a way of adding numerical collisions or numerical diffusion, basically. A lot of people do it. There's been a couple of papers that have talked explicitly about it. And so it has an interesting property when you do this. So I'm going to now use a more Penrose pseudo-inverse because it's a little easier to understand the analysis. And now the deposition takes this form. And so this has a satisfying property that's idempotent in the sense of if you compute what this process of depositing and then mapping back, and you get this expression for your coarse graining operator. And if you apply this again, getting a W double bar, you get cancellation, you simplify, and you get the same W double bar is equal to W bar. So it's a projection, it's idempotent. So it's kind of a satisfying property that there's one unique representation on the grid for any set of particles. Okay, so with that, I can talk about the resampling algorithm. So first, let me emphasize some aspects of particle methods, which you may not think about. But so particle methods really the particles are a mesh for a particle method. They have positions, they have weights, and shape functions associated with them. And so they act exactly like a grid in a more familiar continuum method. So resampling is a form of mesh adaptivity, what we would call mesh adaptivity in a continuum code, and it's useful for some of the same reasons. So in particular, you can place points to be able to maximize your accuracy for the data that you've got, so just optimizing your grid. And another reason that it's useful in a particle context is that it smooths out your particle function, which can be used, and is why resampling or why coarse graining is used in the physics community to be able to smooth out your distribution and reduce particle noise. So particle noise is a problem with particle methods that it's hard to run them for indefinite amounts of time, and so this is one technique of being able to do that. So this, in a sense, maximizes the stability of your operator. However, resampling does, unlike continuum AMR, it does disturb the physics. And so the overall goal in this type of work is to minimize the amount of work for the accuracy and stability, and to minimize the amount of disturbance, if you will, being fairly vague about it, but to the physics. Oh, okay. Okay, so now a resampling algorithm. So you can modify the coarse graining algorithm by, now we're going to be working in full phase space for this. So same equations, but working in full phase space. And now you create, after you deposit onto a grid, you evolve your collision operator if you've got one, and then you create, at this point you've got your distribution function. It's entirely on the grid, and you can throw your old particles away and your old particle weights. And you can create a new particle, a set of particles any way you like. The only thing you have to ensure is that this pseudo-inverse is stable. And so that includes both how you define your mesh, so you can do mesh adaptivity to fit your particles better, and then within that, so you can work with kind of AMR in both with the mesh and the particles to get those to talk to each other. You have kind of both degrees of freedom in the design space to do this. But you just have to ensure that you have this pseudo-inverse property and it'll work. And then you just map back the same process as before, but now you just use your new particle weights. And this is kind of trivially conservative because you've got two things in serial that are both conservative. And so this is also conservative. So today I'm not going to be talking about AMR strategies per se. I'm just going to be talking about sort of the mechanics of doing this. So the examples that I'm going to be using, I'll just use the initial particle grid as the resampling grid every time. This is an example of the grids we'll be using. So this is in 1x plus 1v. So you've got velocity in the y-axis and space in the x-axis with periodic boundary conditions. We use a Cartesian grid. We have simple R adaptivity where we put more particles around where the zero velocity is, where the density of particles is increased for kind of a simple adaptivity strategy. And with this, we have a background grid, and kind of a reasonable way to set this up is you have a background grid, which could be AMR and be complicated. It's just a Cartesian grid in this case. And then you can put a regular grid of particles on each one of those phase space cells. And then that is convenient because it guarantees that you have stability. If you have enough, given the order of your element, if you have enough particles in each cell, it guarantees that you'll have stability in the pseudo-inverse. Okay, so there's a nice kind of corollary, if you will, of the idempotent argument that I just made, and that is that when you do this resampling process, you don't disturb the electric and magnetic fields that you compute when you in PIC. So we can do the same argument of looking at what our new rho bar is, the right-hand side for our Poisson or Ampere's law solve, and it looks like this, and then we can expand out the W bar. And you get this expression, and again, it simplifies, and you come up with on the right-hand side that you get right back to rho, so you don't change the fields when you do this resampling process, which is a nice thing to not disturb the simulation or the model in that way. Okay. Okay. So now I'll talk about some experiments. So this is going to use the Landau damping problem, which is a very popular model in kinetic methods. It's something that involves very subtle physics. If you look at the model itself, there's no collisions, there's no obvious damping, but through very subtle physical processes, you do get damping, and there are analytical analysis of what the damping rates are and so forth. It's a very convenient test, and it's very widely used. It's simply a Maxwellian distribution, so you have a stable distribution of particles or stable distribution, and you give it so this is a Maxwellian in velocity, and then you give it a perturbation in x, and then that thing will it's stable, so it'll just sort of oscillate, and you'd think it would oscillate forever, but it doesn't, it damps. And so there's two forms of the equation that people use for experiments. The so-called linear case with a small perturbation, and a nonlinear case that people almost universally use as 0.5 for the large perturbation. 0.01 is common for the small perturbation, and we'll use 0.01 and 0.10 to the negative 4 to have a very linear problem as well. Okay, so this is an example of these types of things. Let me unpack this a little bit. So this is very common. If you're in this business, you see these things quite a bit. So this is the plot of the electric field amplitude as a function of time. And so in our case, we measure it with the absolute value, the maximum absolute value of a particle, of the electric field at a particle. And so when this thing oscillates, the energy sloshes back and forth between the electric field and the kinetic energy. So the energy in the field goes to 0, and then it goes back and oscillates around. And so you get this absolute value of a sine wave, and you get an easily seen damping going on. So a few things that you see here is one is you can measure, as I said, you can measure the damping rate. And so the first thing that this shows is sort of the efficacy of resampling. So this is showing kind of a convergence plot, if you will, of resampling period, with no resampling being in blue, and then resampling every 1, 2, 4, and 8 time units. And you can see that without any resampling on the linear problem, noise starts to build up, and it just turns to total mess, but about any amount of resampling, you maintain sort of coherent waves. What you see in these now, if you had a perfect model of this, very well resolved and so on, the damping would just go to 0. But the subgrid modes will start to develop unless you have an extremely fine grid, and you get this kind of a rebound where it'll hit and then it'll come back up and do various things. I'll show you some more plots of that. 5 minutes. So this is a very common pattern. So this is kind of what you see. This is the nonlinear case, which I won't go into any detail in it, but I'll just mention that in the nonlinear case, with no resampling, you get this cyan plot that is fairly coherent. So it's not, the resampling isn't nearly as, the necessity for resampling or doing something isn't nearly as obvious or evident with the nonlinear case, or it's a little bit, you can see that it's a little bit noisy, but it's at least reasonably coherent, certainly compared to the linear case. So this is my, if I've got 5 minutes, I can do another slide. But, so this is a convergence study in particle count. So as you increase your particle count, you delay the time that this rebounding happens. So the blue is with the smallest number of particles, and it rebounds first, and then the magenta, and so on, and then you get with the black and the cyan down here are the highest ones, and you get further and further before it rebounds by adding more and more particles. You really have to get down very fine to be able to get it to. We haven't been able. It takes about, well, I can show you. This is. We want to be able to do long time simulations with this. This isn't something I would publish because it's just sort of an experiment to see what the code does. But this is running things out for 1,000 time steps or 1,000 units of time. And similarly, you can see how the blue is the smallest number of particles. It rebounds out first, and then it has this sort of oscillation going on. It sort of starts dying out. But the wave, the small oscillations would then stay coherent for a long time, and then as you refine it, they get kind of smaller, and it delays the onset. And then when it starts getting really fine, it starts to be kind of spiky and kind of different. The largest one with 15 million particles, which takes the black ones here, which takes like 2 weeks to run on my laptop. It sort of looks kind of reasonable. It's sort of going down to as far as it can get, but then it does have this sort of spiky stuff, and then at t equals 500, it kind of blows up a little bit. Or I think it's probably switching modes is my best guess. From like a k equals 1 to a k equals 2 mode, but something's happening there. So anyway, it was just fun to kind of see what this thing would do over a long time, because that's sort of the end goal of this kind of work. Anyway, thank you for attention. I'd be happy to answer any questions.
Questions from the audience? So you mentioned that the behavior of the quote-unquote linear and the nonlinear have different needs as far as resampling goes, right? Is that a fair characterization?
Yeah, so the benefit of resampling is clear with the linear case, the smallest perturbation.
So in terms of applications, are they both going to be relevant when we get to like trying to do simulations for machines or something?
Yeah, so that's a good question. So this is a very simple model problem, right? And I do know that people care a lot about it. I mean, I started working in the plasma people in 2004, and in the 2000s down at PPPL, Princeton Plasma Physics Laboratory, which is sort of the center of plasmas in this country, they would have food fights about particle noise. Like particles of noise are worth. I mean, they would have literally like just screaming at each other. They can be rather dynamic people, and just would you have particle noise, and these things aren't stable. And then that sort of died down. And then we started seeing that people have since the 90s. LaPenta did some very seminal work. And this was actually formally kind of similar to this, and it has something that looks a little bit like a pseudo-inverse. And resampling is really the way you deal with particle noise. So people have at least cared enough about it to argue about it vociferously. And when I've told people that I'm doing this, they're kind of like, well, we only worry about short time physics. It's like okay, so.
Getting to that, for the nonlinear, is it possible that the noise affects it and it changes things? It's just hard to tell.
Yeah. And I'm not really doing anything other than just sort of eyeballing it in these kinds of things, yeah.
Cool. Let's thank Mark again, and we'll start getting set up for our next speaker.
You want to give Hansel the mic?
Yeah, so we got to get your mic off and get that.